Geometry. On Wednesdays, we wear pink. The 23rd of September. SWBA students will be able to use inductive reasoning to make conjectures. So inductive reasoning is going to be this type of thinking or reasoning that we're going to use to make a conjecture. We'll learn what they both mean, okay? So first of all, first things first, not only am I the realist, I'm going to write my name. Me llamo Profe Castle.
This is not Spanish.
Okay? Oh. Lo siento. Okay. So you can put your class period, you can put the date in there if you want, you can put the topic if you want. I'm most concerned that your name's on this. Okay? Inductive reasoning. Inductive reasoning is making a conclusion based on observations and patterns, is it?
Yeah.
It's like it just magically appears on there, huh? Ooh, probably is. All right. So it's making a conclusion based on observations and patterns. Okay? So we do this a lot, actually, without even realizing it's called inductive reasoning. Let's say in elementary school, you guys probably lined up a lot to go to class, to go to recess, you name it, right? Okay. A lot of times the teachers had you lined up in a specific order, didn't they?
Yeah.
Like first name, last name, or they might have had you lined up like this. There's a boy. There's a girl. There's a boy. There's a girl. There's a boy. There's a girl.
We don't got that many girls.
What do you think would come next? Who do you think would come next?
Girl.
If the last one was a girl, who do you think would come next?
Another girl.
Probably a boy. Why do you say that, Ray?
Because it went girl, boy, girl.
Because it kept alternating, right?
Yeah.
So we're going to predict that based upon what happened, based upon our observation and the pattern we're going to see, we're going to make a conclusion. We're going to see that the next person would be a boy, followed by a girl, followed by a boy. So unless something interrupts that. So we're going to make our conclusion based upon this observation and pattern. That's inductive reasoning. It's saying, based on what I've seen so far happening, this is my prediction for what's going to happen. Let's say, for example, I have a student that consistently doesn't turn in homework.
Let's go.
Okay, believe it or not, I have a couple of those. Okay, so I have a student consistently doesn't turn in homework. Based upon my observations, based upon their pattern of not turning in homework, what's going to be my conclusion when I hand them the next homework assignment?
They're going to have to yell at them to turn in their homework.
They probably won't turn it in. Okay, let's say I have a student who always does their homework. Okay, based on my observations and their pattern of doing homework, when I hand them a homework assignment, what do I think is going to happen?
They're not going to turn it in because
They're probably going to do it.
you never seen
Okay, now does that guarantee it's going to happen? No, but it's our guess. It's our conclusion. It is our conjecture. A conjecture is a concluding statement. Did you like that transition?
That was a good segue.
Okay, it's a concluding statement reached using inductive reasoning. It's the conclusion we get to by inductive reasoning. So inductive reasoning is the process that's saying we're going to make a conclusion based upon our observations, based upon these patterns. Conjecture is that conclusion. So based upon me seeing this line alternating boy, girl, my conjecture is that the next will be a boy or a girl based upon what the previous one was. Based upon the student's pattern of not doing homework, my conjecture is that they won't do the next assignment. Based upon the student turning in everything on time, my conjecture is that they will continue to turn in their stuff on time.
What if they don't want to?
Well, then my conjecture would be proven false.
You actually think about that kind of thing. Like you do homework.
I mean, it's kind of, yeah, I know it.
Nice.
Yeah, you have a pretty good guess by the time the unit's over. Not all the time that people can change for sure. I've had students change throughout the semester. Maybe a student who didn't start off on the best foot, they turn into having a great end of the semester, or vice versa. Continuing on, we're gonna practice. So we're gonna be given a pattern. We're gonna be given the first 4 terms, so to speak, each term, first term, second term, third term, fourth term, in the pattern in this sequence or series. We're going to be given the first 5 terms of the sequence, And then we're going to be, given the first 4, we're going to try to find the next 5 and try to make a conjecture about what's happening. So if we're given these terms, 38, 31, 24, 17, raise your hand if you have a guess or a conjecture as to what my next term might be. Chase. 10. Why do you say 10, Chase? Because we're subtracting 7 each time. 38 to 31, subtracting 7. 31 to 24, subtract 7, subtract 7, subtract 7. I'd agree with that. Anybody else have anything different?
No.
That's good.
Yeah,
I would.
do have something.
What do you have?
24, ha.
Nice. Okay. I don't think it's part of the pattern, but that is accurate. Okay. What would follow next after 10 then? 3. What do we think would follow after 3?
-4.
Then?
-11.
And then?
-18.
So we keep subtracting 7. So we could say our conjecture is that we subtract by 7. Subtract by 7. Maybe subtract by 7 each time. Just to clarify, that doesn't just happen once. Okay? A more fancy way to say it, you could say is to generate the next term, subtract 7 from the previous term. That'd be a fancy way to say it. To generate or get the next term. Generate just means get or create. To generate the next term, subtract 7 from the previous term. So you take whatever term came before, subtract 7. Okay? What about number 2? 2, 5, 11, 23. 2, 5, 11, 23. Let's look at this. Let's see if we can find a pattern, okay? Okay, so you're noting we're adding by...
Multiplying by 2.
We're what?
Doubling it every time.
We're doubling what we add by. So we add by 3, double it, add by 6, double it, add by 12. Okay, so what do you think we might come next? What?
47.
Okay. Add by 12, so double it, add by 24, get 47. Okay, Ray, what would you say? Would you get the same number, 47?
I got something with it.
Okay, no, what did you do? There's multiple ways to do this one. That's why I'm asking you.
Well, I looked at it and I thought they were multiplying itself.
Yep.
And then adding 1.
Okay, so we could be doubling it and adding 1. What's 2 times 2?
4,
Plus 1?
5.
What's 5 times 2?
He is right.
Plus 1. And could that work here too? 23 times 2?
Yes, sir.
46 plus 1, 47. So either way it could work. So we could double what we're adding to it, or we could double the term and then add 1. There's both ways of saying it. So whatever one you have is okay. As long as you can back it up, we're good with it. As long as you can back it up, we're good with it. What would be our conjecture here? What would be our conjecture here? Can anybody have an idea then? It could be either one of what was said. Kenny.
Okay, so it's either increasing what you multiply is increasing by itself every time, or you multiply by 2 and add 1.
Okay, I don't know how to word your first one, but multiply by 2. I'll write that one down though. Multiply by 2, comma, then add 1. It might be good to clarify that you have to multiply first, then add. Okay. Dayton, how would you word what you had said?
I worded it like start with and then doubling it.
Okay. So start by adding 3. Then double what you add each time. Do you need both of these?
No.
No, just one of them.
Oh,
I'm not a bar of soap if that's what you're trying to say. Okay, Ryder, how about doing clean?
So like, I'm just wondering, like, I don't understand how this would like be useful in math because like we're making a prediction of a pattern, but it's not set in stone because math can always like, yeah.
Sure. So this pattern, it could end up changing. Like what happens, like this one should be 47, but we still have to find the next term.
95.
So it should be 95, but what happens if it was like 94, right? We'd have to go back to the drawing board and try and find another scenario that might work. It'll be useful for math later because we're using this to help us with our way of thinking. Once again, we're trying to format and trying to create up a new way of thinking and reasoning through it. And so this is part of that we're going to use. Does that make more sense, Ryder? That's a fair question, though. What will come after 95, guys? Do we have to double 95 and add 1? What's double 95?
191.
It's 190 plus 1 is 191. What's double 191?
I don't know.
Chase? 382 plus 1 is 383. And what would be our fifth term? Our ninth term total? 767. Very good, Kevin. And we could keep going, couldn't we?
Yeah.
They'd get harder and harder to get to, but we can keep going. Okay, that's the whole point of a series or sequence, is they could keep going.
I got 766. Hard.
Okay, I think you just doubled it. But then you have to add 1 to it.
Yeah, I did.
All right, let's look at number 3. 1, 4, 9, 16.
It's random.
1, 4, 9, 16.
Nothing.
They're not all odd, because 1 and 9 are odd, but 4 and 16 aren't.
Yeah, I'd look at odd number 2.
Okay, so our next one is probably going to be odd. Okay, so Landon's saying, based on what we're saying, next one might be odd, followed by an even. Okay, Ray, what are you thinking?
So I think so you do 1 plus 3, you get 4.
Okay.
4 plus 5, so 3, 5, 7, 9.
Okay, so you're adding by the next odd number, maybe. So what would you add 16 by? So we're adding by 3, adding by 5, adding by 7.
And then 9, so that would be 25.
Okay, 25. Okay, that could be one way to do it. There's also another way to do this. Okay, there's also another way to do this. Dayton.
1 plus 2x.
Okay, 1 plus 2x.
Because you you start with 3, then you go to 5, 7.
It's multiplying.
Oh, okay. So for each term, I get what you're saying. Yeah, that could work. That could work for the actual the rule. Okay, 1 plus 2x would work for the rule. We're not going to talk about those today, but that would be the rule. Okay, or it could be a version of the rule.
How
What?
does that work? Because if it's 2x plus 1, then you have to multiply 2 by 1.
Oh yeah, so you'd have to call this term 0 and then call this term 1 maybe. Yeah, or it could be 2x minus 1. Maybe might be a good way to get to work. That's a great question. All right, so we could add by 9. What about perfect? Oh, Ryan? They're all perfect squares. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. Kevin, what's the next square?
36.
36. Come on, you know these. Keep it coming. Keep them coming.
49, 64.
81.
All right. Kevin was beast mode with these last year. Okay. He was really good. He even beat me in a time competition once. He beat me in a time competition of the perfect squares. Did we do 1 through 20 or 1 through 25? 1 through 20.
Bad.
All right, conjecture. So what we had 2 different things we could say. So one of them we said was that we add by the next odd number. But what do we start with?
Perfect square.
Add by the next odd number starting with what number?
3.
Starting with 3. The first thing we started with was 3. Right, you're thinking in our term the 2x plus 1. What could be our other conjecture? Perfect squares.
Autobots? I definitely heard Autobots.
Roll out, okay? So those could both be conjectures. So this goes to show on some of these, there's multiple ways to think about it. And they both would hold up true. Add by 9, add by 11, 13, 15, 17. Okay? Ryder.
So if you chose to do the perfect squares, is just saying perfect squares too vague? Because like it could have been perfect squares, but going backwards.
That's true. Okay. So, maybe we could put consecutive perfect squares. Okay. So maybe we could put consecutive perfect squares or use the next perfect square. That's a great point. That might be too vague. Just saying perfect squares might be a little too vague. So it can be good to be a little more specific with it. Bless you and bless the rains down in Africa. Let's forget. Thank you for bringing that up, Ryder. That could be a little too vague. Any other questions on these so far? All right, I want you guys to try number 4 here. Number 4 here. A, D, G, J. Raise your hand if you think you might have what's going on here. Quentin.
2 of the letters every time.
Okay, so you're skipping 2 letters every time. I would agree with that. Okay. Okay, so skipping 2 letters every time, using the next third letter or the third next letter. They're both ways of communicating the same thing, right? So skipping 2 letters each time or using the next third letter might be a good way of putting that. Kenny?
I wrote just every third letter.
Okay, every third letter, same idea. Those are all really saying the same thing. Okay, where are we going? Okay, those are all really saying the same thing. A, D, G, J. What would come next?
L-O-R-U-X.
M. Okay. J, K, L, M.
P.
N, P, O. Or, excuse me, M, N, O, P. Excuse me, I skipped O there. N, O, P. Q, R,
S.
S. T, U,
V.
W, X, Y.
Y. O.
Okay? So anything along the lines of skipping 2 letters each time, every third letter. Okay? Anything like that. That makes sense? Those are both really saying the same thing, but they're different ways of approaching it. Kenny?
May I use restroom?
Yes, you may.
Thank you.
All right. I want you guys to try number 5.
My dad.
Oh. All right, let's look at number 5 here. Raise your hand if you think you might have this one. Okay, Bailey, what are you thinking?
It's adding by 25 minutes.
Yeah, it's adding by 25 minutes every time. I'm seeing this on Presley's one right now, too. It's very good. Add by 25 minutes. Each time, or every time. So do you have to word it exactly how I do? No, there's some freedom there. So 7:30, 7:55, 8:20. What would come next? 8:45. Ian, what would come after that?
9:10.
Thanks, Ian.
Oh, my bad.
Ian, what would come after 9:10? It's okay, it's okay. Okay, 9:35. Thanks, Ian. Thanks, Ian. Ian, what would come next?
10:25.
10:25. Man, so many Ians in here. I need to change people's names. Alrighty. 8:45, 9:10, 9:35, 10, and 10:25. Now, if you messed up one of these, what would happen? You messed up all of them, okay? So you have to be careful as you go through these. Sometimes that can happen, right? You mess up one, and you might get off 5 minutes or 10 minutes, okay? And all of a sudden, oh my gosh, snowball effect. It's bigger as it goes down. You make more mistakes as you keep going, okay?
How's it a butterfly?
Yes. Dyslexia. Okay. Number 6. We're actually going to skip number 6. Okay?
I figured it out.
Questions on this page. Okay. Counter. What does counter mean? Besides like a kitchen counter, what does counter mean? Okay. Maybe dodge. Maybe a little bit different than a dodge. What?
Send back.
To send back. Maybe the opposite of it. Okay. That's kind of what I'm thinking. Kind of going opposite. It's opposite. What does it mean to counteract something? You're preventing it from happening. You're kind of doing the opposite. You're going against it. Okay? It's going against it. So we have an example. Examples are things that we know demonstrate something, right? They demonstrate something. They show something. A counterexample is going to be going against the example. Okay? It's going to be showing it's not this. An example is showing what something is. A counterexample is going to be showing what it isn't. So a counterexample is it's still an example, but it is an example.
That proves things wrong.
Yep, that shows a conjecture is false. It proves things wrong. It shows a conjecture is false. Oh.
You're talking about how you went your socks last week.
Oh, yeah. I didn't go get hamburgers, but one of my friends did, and I'm getting burgers because of it. So, maybe.
Should have made them at home.
Have you went to Buffalo Wild Wings?
I'm not a big fan of B-dubs. I don't like wings that much. So here's the thing, okay? I don't really like the sauce as much. The actual wings are okay, but here's the thing. If I don't care for the sauces, then why would I want such a small amount of meat. You know, I'd rather go with like, you know, something like, you know, tenders or strips or sandwich or, you know. Yes. So, so it's an example that shows a conjecture is false. Here's the thing for a counterexample, guys. You only need one for it to be false. So when we say something's false in this class, we're going to be saying it is at least not true once. So it's either it's always true or it's false. Does that make sense? We're either saying it's always true or it's false. We're not talking about sometimes here. Sometimes we're going to say it's false.
Oh, that's false.
When we say this is a conjecture, we're saying this conjecture is always true. We're testing it. This one's always true. And so if we can find even just one example where it's not true, one counterexample, that shows it's false. So in these examples here, we're going to determine whether the conjecture is true or false. We're given a conjecture in these. We're going to say that's true or it's false. If it's false, we have to provide a counterexample. That's our explanation. To say, here's why it's wrong. The sum, what was that? The sum of any two consecutive integers is always odd. The sum of any two consecutive integers is always odd. Let's look at what this is talking about. The sum. What's sum? Addition. Of any two consecutive integers. What's consecutive mean?
It's out of 90.
Nope.
Like it comes after.
They come after each other. You're thinking complementary. Consecutive means they come after each other. So the sum of any two consecutive integers. Integers are positive and negative whole numbers as well as 0. It's saying if you take any two integers that follow each other, you're going to get it to be odd. Is that true or false?
False.
Okay, false. Ray, tell me why it's false.
Because like you have 0, 2, 4, 6.
Okay, 0 and 2 are 0 and 2 consecutive.
Yeah.
Do they follow right after each other?
No.
Okay. So we can't add 0 and 2. Okay, Ray?
Right.
Oh, we want to go to the restroom.
Yeah.
Okay, good luck.
It's true.
It's true.
Wasn't mentally ready for that.
Can we think of any examples where it's wrong? I can't think of them. Let's try some out though, just in case. You don't need these for your work. This could be your answer. But let's try some out just as we're figuring it out. So let's try some different scenarios. Let's try maybe two negatives. Well, -2 plus -1, that'd be -3. That's odd. Maybe let's try a negative and 0. -1 plus 0, that's -1. That's odd. Well, maybe 0 and a positive. We'll try some different scenarios. 0 plus 1. That's 1. That's odd. What about two positives? 1 plus 2. I did plus 2. 1 plus 2. 3. Well, that's odd. So we're trying all sorts of different scenarios here, right? We're not just continuing to try the same two things or the same thing over and over. We're trying different scenarios. So let's try a negatives. -0. 0 positive. 2 positives.
-0, -1, positive 1, -0, positive 1.
0 can't be negative or positive. Okay.
Same spot or different spot?
Okay. You're in that brown desk. Okay. Tyler, do you want to grab a packet of white notes on the very corner of my desk? Okay, it's a thick stack. Okay, Kenny.
Can you record your lesson from the tablet?
Yes.
Be louder? Oh,
Yes.
That's cool.
It is pretty cool.
That's awesome. Thank you.
Yeah, it's like ice cold. Okay. So
What if I want to like French cool?
that's too bad. Okay. So this is always true. There's nothing that can prove it wrong. Okay. Thank you. Okay. I'll have you put it in the very top tray. Okay. Number 2. The product of two numbers is always larger than either number. The product of two numbers is always larger than either number. Product is asking what? Product is telling us to do what?
Multiply.
Multiply. It's saying whenever you multiply two numbers, any two numbers, it's always going to be larger than either of the two. Think about this for a second, whether that's true or false. And if it's false, think about why. What's an example? Okay, Ryder, what are you thinking?
It's false.
Okay, why do you say it's false?
Okay, yeah. It's say you take 6 multiplied by 0.
Okay, 6 times 0.
That's not larger than 6, and it says larger than either.
Yeah, very good. 6 times 0, that's multiplication. You get 0. Is 0 larger than either of these numbers? No, but it has to be larger than both, and it's not larger than any of them. Okay, so that could be something that proves it wrong. Kenny.
You're not going to prove it true.
Wait a minute.
So Kenny, once it's
Okay,
even
so-
proven wrong once, it is false.
No, I was gonna say. So I was. So I I was definitely trying to prove it wrong,
Yeah.
but I said it was.
So you got something that came up with it being true?
I misread it backwards. Is what I did.
Okay.
I
Now, there's other examples, too, where we could prove it wrong. Okay, Dayton.
Multiplying by a decimal.
Multiplying by a decimal. Okay, decimal less than 1 could work. Okay, so maybe like 4 times 0.5. That'd be 2. Okay, well, 2's not larger than 4. Kenny.
-1 times 2.
Negatives. So negatives could work. Okay, so maybe -1 times 2. And that could be -2. Well, that's not larger than either of those numbers. It's smaller than both. Okay, Bailey, you stretching?
Yeah.
Okay, another example could be multiplying by 1. 6 times 1 is 6. Well, 6 is larger than 1, but it's not larger than 6. So there's multiple counterexamples here. Now, do you guys have to have all of these? No, you literally just need one. Anytime you can even provide one counterexample, it shows it's false. Okay, questions on this one? Dope. 3. The product of 2 perfect squares is always a perfect square. The product of 2 perfect squares, if you multiply 2 perfect squares together, you're always going to get a perfect square. That's what it's saying.
No.
Is that true or false?
False.
Okay, give me a reason why.
2 perfect square of 4 is perfect square of 9.
Okay, 4 times 9. Those are perfect squares. That's 36. Is 36 a perfect square?
No, sir.
I think it
Mm.
is 36.
Actually, yeah, it is.
Perfect square.
Yeah, 6 times 6 is 36. So that was not a counterexample. Can anyone else think of a counterexample?
It's true.
It is going to be
Hey,
true.
if you don't stop being right.
It is going to be true.
The trend on this is true, false, true.
Oh, so you're making
Make your,
an you're using inductive reasoning.
it's gonna be weird wrong.
Okay. 4. The area of a rectangle. The area of a rectangle is 6 square meters. Then the dimensions must be 2 meters by 3 meters. So if our area is 6 square meters, our dimensions have to be 2 meters by 3 meters. Okay? Ryder, what are you thinking?
Well, I don't know if it means in the order of 2 by 3 because it could be 3 by 2.
Okay, so it could be 3 by 2.
Or it could be 1 by 6.
Okay, it could be 1 by 6. Okay, it could be 1.5 by 4. Okay. Can you put it in the very top tray, please? And I'll have you hold on to the calculator. Thank you, Cleo. So this is false.
Is that 1/16?
By. That's a really bad B.
Okay. I was mildly confused.
I could tell. I don't know if that made it better or not. But it's 1 by 16.
Now I'm dark.
Yes.
Very good.
Okay.
Here's possible.
Yes.
1 by 6 wouldn't work because that would be 7.
So for area, we multiply. So you do 1 times 6. Yeah. What? Why are you calling people nerds for stuff?
Why not?
Call me a nerd for like an M&M.
Well, that's 'cause
Like,
you're a nerd.
I mean,
M&Ms are good.
whether or not the rapper, but those different story. I mean that's fair. She wasn't here for she wasn't here for it.
Yes, she was.
No, she wasn't.
I wasn't in here.
No, she wasn't.
I don't know. Okay.
5. Dividing by 2 always produces a number less than the original number. So if you take a number, divide by 2, your number is always going to be less than the original number. Think about it for a moment without blurting.
False.
Think about it for a moment without blurting. Okay, raise your hand if you think you might be able to help with this one. Okay, Bailey, what are you thinking?
I think it's true.
You think it's true? Why do you think it's true?
We're dividing, so even whatever we get for a product, it's always going to be bigger than the original number.
Okay, so you're saying we're dividing. Dividing makes things smaller. It takes things and makes them smaller. That's why you have less something after you divide or put it in groups. Okay? Elizabeth, you shook your head. Why'd you shake your head, Elizabeth? You don't think it's true. What do you think it is then?
False.
You think it's false. Elizabeth, why do you think it's false?
Well, I was trying to think of a number in my head. But I'm like, I'm
Okay, you're having trouble thinking of one? Maybe Seth can help us out.
2 divided by 0 equals 0.
Okay, but we're dividing by 2. We're not dividing 2 by
0
things.
divided by 2.
Okay, 0 divided by 2.
We can't even divide 0.
You can take 0 divided by things, but you can't take anything divided by 0. 0 divided by 2 is 0. Is 0 less than the original number 0? No, it's the same. That proves it wrong. Do we need to do any more counterexamples? No, but could we? Dayton, what else could we do?
Nothing.
Okay. What about...
I got something.
Okay, Ray?
Negative 14 divided by 2.
Negative 14 divided by 2 is negative 7. Is negative 7 less? It's bigger. So that's another one. So 0 or negatives. It works for positives, but not 0 or negatives. Okay, questions on that? Okay, Dayton, is our true, false inductive reasoning working out? Darn it. Okay. Vertical angles are never complementary. Vertical angles are never complementary. Okay, reminder of what vertical angles are. Vertical angles are these angles that make an X. Okay, so it'd be like located here and here, and they're always congruent. So these are congruent angles, and it's saying these vertical angles are never complementary. Complementary means what?
Never 90.
They add up to 90. Kenny, what are you thinking, buddy?
That's gotta be false.
Why do you think it's false?
Because they can be like 45. Yeah.
Because they could both be 45 degrees. They have to be the same,
Yeah.
but as long as they're both 45, that's one time when they're false. It's only one time, but that's all we need. They could each be 45 degrees. That proves it wrong. Okay, let's look at number 7. If A times B equals 0, then either A or B equals 0. Elizabeth.
It could be like.
Yep. If two numbers are multiplying to equal 0, we're saying one of them has to be 0, at least.
No. Yes.
Okay? Kenny, give me the time when you multiply two numbers together, you get 0, and one of them isn't 0.
Negative 2 times negative 1.
What's negative 2 times 1? Negative 1.
Or I mean negative 2. Negative 2 times negative 2. Negative.
Negative 2 times 2?
Yeah, that.
What's negative 2 times 2?
Negative
0. Right.
That's negative.
You're adding them. This one is true.
I thought it was like.
There's no way you can multiply to get 0 without at least one of them being 0.
Even if they happen
It would still have to be 0.
Yeah.
Yeah, because the exponents are just repeated multiplication.
Oh wait.
Okay?
No. You could have an ex. Oh wait, no, an exponent of 0 is set to 1. Yeah.
Okay? Two angles supplementary to the same angle must be congruent. What's supplementary mean? That's 180. So let's say, for example, I draw a picture. Pictures can help. I have two angles, and they're both supplementary to the same angle. So they're supplementary to add to 180. So let's say this one's 130 degrees. What would this one have to be?
60.
Try again. 50. Now, if I have another angle supplementary to this one, what's going to be the measure of that one? So we're saying if these two angles are both supplementary to the same angle, so two angles supplementary to the same angle, these two angles are both supplementary to the same angle, they have to be congruent. Is there any way to have these two angles be supplementary to our third angle and for them not to be congruent?
No.
There's no way. Because if they're both supplementary to this one, they have to be the same thing. Because you can't have two different things adding up with the same number to 180. So if an angle is 120, only one thing's going to add to it to be 180. If an angle is 40, only one thing's going to add to it to be 180. So if two different angles add to 180 with it, bless you, bless rain down in Africa, let's forget, they both have to be the same. So this one is true. This is the last one we'll do. We'll skip 10 actually. All state names have at least 2 syllables. Think about it. Don't blurt. All state names have at least 2 syllables. Be careful with the wording, okay? All state names have at least 2 syllables. Syllables. Nebraska. 3 syllables. Okay? Raise your hand if you think you have an answer to this one. Okay? Let's go with Dayton. Okay, false. Maine. How many syllables does Maine have? 1. It's the only state with 1 syllable. It's the only one that can prove it wrong. Maine. Maine has 1 syllable. You're like starting to go through them. Alaska, Alabama, Arizona. Anyway, okay.
You know what that was the main issue with this problem.
Ha 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 ha.
Hardy, hard.